So good morning, everyone. Welcome back to Math 115. So today we are going to talk about section 4.4 and section 4.5, excuse me. So you have a homework assignment which is due on Friday. I'm going to post the 4.4 homework. I'll post it. It'll probably be due maybe Tuesday. Can I make something due on Tuesday? It's election day. Should I make it due on Monday instead? I'm just going to make it due on Tuesday. If you want to do it before then, you can do it before then. So that'll be 4.4 homework. I'll post that hopefully today. Quiz 6 is going to be on Wednesday next week because, again, we have Tuesday off, so we won't have class that day, so no quiz that day. But we will have a quiz on Wednesday, November 9th, and it will cover sections 4.1 to 4.4. Regarding my office hours, I will have office hours today from 2:30 to 4. I'm going to try to do them again in the Math Learning Center, LeConte 102. It's really convenient. We got those hexagonal tables in there. It's good for group work and stuff. So that's where I'll be today from 2:30 to 4 p.m. Okay, any administrative questions before we start in on content for today? I gotta clean my glasses. For some reason I got a massive smudge. Oh God, I made it worse.
I have glasses. Yours are long.
That's okay. I think we're good. Okay. So let me remind you what we talked about last time. So again, we've been toying with this idea of graphing the trigonometric functions, okay? So again, there's nothing, there's something strange about this function, but I just want to remind you all that it is a function, right? What does a function do? A function takes an input and it gives us for each input an output. So if we have a function, okay, just because this function is defined in this kind of silly way where we put it inside of this circle and we go to this point and we look at the coordinates of that point, it's still a function. And any function who I take inputs as an input and I give an output, right? We can take a look at the graph of that function by just putting all of the inputs on the horizontal axis, and then we make the height of the function whatever the output of the function is for that given input. So for example, for sine of pi over 2, the input would be pi over 2, so what do? We ask ourselves, what is the output of the sine function? And that's what we're going to make the height of this function. Well, to get the output of the sine function, what do I have to do? I have to take pi over 2, I inscribe it in, excuse me, I inscribe it inside of the unit circle, and I go to the point which is pointed at by that angle, and sine's job is to give me the y-coordinate, right? Which in this case is 1. So that's how I choose to make the height of the function when the input is pi over 2. Should be whatever the output of the sine function is for that input. Okay, so this is how we can make this, and it's not hard to see that this function is going to repeat this section of the graph over and over and over again. Why? Because if I go past 2 pi, okay, then I have gone basically all the way around the circle and then some. I'm going to start pointing back at points which I have already pointed at, right? For this case, for 9 pi over 4, that is the angle shown in red on the unit circle. It's the same as the angle pi over 4 because, well, it's not the same. I shouldn't say the word same. What is the word I should use? It's coterminal. Very good. It's coterminal to this angle pi over 4, which just goes up a little bit. They both point at the same point on the unit circle, so the output of the trigonometric functions will be the same. Okay, so sine and cosine are periodic functions. That was the word we used. It means that if you draw a line segment like this of length 2 pi, okay, if this length is 2 pi, then that represents going around an additional 1 time on the unit circle, yes? And that means we're going to have the same point, which means the output of the functions, the sine and cosine function, will be the same. Okay, are there any questions on graphing sine and cosine? Okay, doesn't seem like there are. So then what did we do? We had a partner practice where we tried to use this information that we had about the graphs of sine and cosine to get the graph of tangent, which the graph of tangent can be seen here in pink for, what did I say, from 0 to 2 pi. So it looks like this here, and then it comes up like this. So we have vertical asymptotes, right? We have vertical asymptotes. And how did we figure out the behavior of the function near the asymptote? Well, we check, basically, what is the limit as x goes to pi over 2 from the left of tan of x, or tan of t, or whatever. So then we have limit. Also, we also want to check what is the limit as x approaches pi over 2 from the right of tangent of x. So this means from the right, and this means from left. So what does that really mean? What it means is I'm going to take inputs which are very close to pi over 2, but less than pi over 2 for this one. Or I'm going to take inputs which are very close to pi over 2, but more than pi over 2. And I'm going to see what's going on with the function. And it's not hard to see if you compare the graphs of cosine and sine. So where is pi over 2? It's like right here, right? Or on this one, it's right here. So what's happening to the denominator? The denominator is getting closer and closer to 0. So the denominator is something like very small, but positive, yes? And then the numerator, which would be sine, is going to be very close to something like 1. If we take a number like close to 1, divide it by something very small and positive, I'm going to get a number which is big and positive, okay? Then you can ask, well, what's going to happen when I approach from the right? Okay, so if I'm going to take this path here, well, the numerator is getting close to 1 again, and the denominator is getting close to 0, but crucially, the denominator is getting close to 0 from below, which means we're going to divide a positive number by a very small negative number, which would give us a very big negative number. Is there a question? Are we good? Okay. All right, so that's what's going on with the graph of tangent. That's why we observe an asymptote. And you're going to notice that this one is also going to have this kind of repeating phenomenon. Except we're not going to be repeating on a period of 2 pi, we're going to be repeating on a period of pi. Why is that? That is because you are going to see the same ratio, okay? You're going to see the same ratio of y to x across the origin like this, right? Why? Because this is going to be the point xy. If this is the point xy, then this is going to be the point negative x, negative y. And when you divide the y-coordinate by the x-coordinate, you'll get the same thing for each of these, right? So if you draw a straight line through, you can call this a chord if you want, or a diameter. How about a diameter? If you draw a diameter, the points will have this kind of a relationship to one another in terms of their coordinates. So when we take the y-coordinate divided by the x-coordinate, we're going to get the same thing. Okay, same deal if I were to take, say, this point and this point, okay? This point will have coordinates x, y, and the coordinates of this point will be negative x, negative y, whatever those might be, right? So again, we're going to get the same thing. So if we cross straight across the unit circle, i.e. if we add pi to the angle, right? If we add pi to the angle, then we're going to get the same result for tangent. Okay, so sine and cosine, we have to add 2 pi, i.e. we have to start here, go all the way around before we get that answer again, right? Before we get that answer again. But for tangent, anytime that I just go an extra pi units, okay, an extra pi units, then I will get the same result because of that special relationship between points which are symmetric about the origin. Okay. Any questions on the graph of the tangent function? Okay. Then it doesn't seem like there are, so let's move on to today's material. So I want to talk about transformations of trigonometric functions, right? So remember way back when we learned all of those different ways that we could move a function up, down, side to side, squish it, stretch it, bop it, twist it. We can do everything, right? Okay, so let's take a look at how we stretch vertically. Well, of course, vertical stretch is going to have the same type of thing. If we multiply by a number a, okay, we're going to have either a vertical stretch or a vertical shrink, depending on whether a is, okay, if a is bigger than 1 in absolute value, it's going to be a stretch. If a is less than 1 in absolute value, it's going to be a shrink or a compression, however you want to say it. And what are we going to do if a is negative? Yeah, flip. That corresponds to a vertical, i.e., okay, vertical reflection, i.e. about which axis? Y-axis is this one, so if we do a reflection about this, we're going to be going like this. What kind of reflection would that be? That would be a horizontal reflection. So even though we're doing a vertical reflection, that means we're going to we're moving things up and down. That means it's going across the x-axis, actually. I know it's really confusing because you think vertical y, but in this case, the vertical reflection is going to take us across or about the x-axis. Okay, so let's see what's going to happen. Well, we're just going to stretch by a factor of a, and we know how high sine gets. How high does sine get? It goes up to 1, and then maybe down to -1. That's as big as it gets. So let's do something like, let's do an example with a equals to 3. What would that look like? Well, basically, I know that the peak of this thing, okay, and actually every single point is going to have its height multiplied by 3, okay? So I'm going to do, here's 2, and here's 3. So what's going to happen is I'm going to stretch this thing in this direction, and I'm going to stretch this thing in this direction, yes? So I also need -2 and -3. So what's it going to look like? Well, this point is going to be transported up to here, because its height gets multiplied by 3, and so too do all the other heights of all the other points. And I'm still going to pass through the x-axis at this point. Can someone explain why?
Multiplying 3 by 0 is still 0.
Exactly. Very good, Gavin. Multiplying 3 times 0 is still 0, so it's still going to pass through right here. So just because we're going higher doesn't necessarily mean we need to go further, okay? It means we're just going to take the height of every single point and multiply by 3. So we go through the x-axis at the same point, and then what? This point needs to get transported down to here. Okay, so I'm going to do something like this. And then again, through at this point. Okay, so what did we do? We just made the height of the wave bigger, basically. That's what we did. We made the height of the wave bigger. And we can make it smaller too if we multiplied by like 1/3 or something like that. And then if we were to multiply by something negative, if I did -3, what would it look like? It would look like this, yeah? So we'd flip. Okay, that would be what we would get if we flipped. Any questions on that? I think we've been doing vertical stretches for a while now, but it is strange to see it now coupled with a trigonometric function, right? But it's really just the same process. So any questions on that? Okay, by the way, the word we use for, there's a special terminology we use for this height, okay? This height, the word we use for it is, anybody know it? Sorry? P, oh no, is A for the word amplitude. In this case, it's 3. We measure from the x-axis to the top of the tallest point of the wave. We call that the amplitude of the wave. Okay. So the amplitude of sine and cosine normally is 1. And if we stretch by a factor of A, then the amplitude will be instead absolute value of A. Okay, so that's that. How about stretching horizontally? Well, we can do that as well. So we have, again, a multiplication by A, this time on the inside. So if A is in absolute value bigger than 1, what kind of phenomenon am I going to see in the graph if A is bigger than 1 in absolute value? So what kind of phenomenon am I going to see on the graph? How is it going to be changed if I multiply on the inside by a number which is larger than 1 in absolute value? Yeah, it's going to be a horizontal shrink. Okay, so what we have to remember is we think, in our mind, we think, well, A is a number bigger than 1. That makes me think stretch, right? But you got to remember, where are we? We're on the inside. The inside is like opposite world, right? Everything is not the way we think it's going to be. When we add by a number, we move to the left instead of to the right. It feels like we should go to the right. It feels like right now we should be stretching. But we're not going to stretch because we're on the inside. We got to do the opposite of what we think we should do. So this is going to give us a horizontal shrink. If you want, the way you can think about it is if this is x, where is ax? If a is bigger than 1, then ax is further away. So what are we going to do? We're going to move the height of the function from here. We're going to transport it backwards, right, towards the y-axis, okay? So if you think about it that way, it's like you're taking stuff from further away and you're bringing it closer to you. And that's one way to visualize it if you want. Okay, so if a is less than 1, we have a horizontal stretch. And if a is negative, what's going to happen? What's going to happen if a is negative? It can be determined. Good guess, though. What is going to happen if a is negative? How is that going to affect things? Yeah, Sully's got it. It's going to be a reflection. So just like from above, when a is less than 0, when we multiply by a number less than 0, it's like multiplying by a negative, right? So if we have a negative sign inside, the negative sign is going to cause us to have a horizontal reflection, which horizontal reflections are about the y-axis. Okay, so let's do an example again. Let's do a equals to 2. So let's do the graph then of sine of 2 times x. So what do I have to do? Well, this point is going to get basically transported backwards, right, towards the origin. Okay, so I'm going to take everything and I'm going to shrink it by a factor of 2, right? So what's going to happen is I'm going to pass through the x-axis here, and then I'm actually going to finish the whole curve right here, right? This point's going to go back to here because that's halfway back. This point is going to go back to here because that's halfway back. So it's going to look something like, the height will still be preserved, okay? The height will still be preserved, but we're going to do it twice as fast, I guess, if you want to say that way. Okay, so same height, same amplitude, but the period is much shorter, right? The period is the length of time that it takes for us to repeat. So the period is now 2 pi was what our original period was, divided by 2, which is pi. So this was our original period. So if we do a shrink by a factor of 2, we take the period and divide it by 2 in order to get the new period, which is pi. So that's how long it's going to take until I repeat. So once I get to here, what am I going to do? I'm just going to keep going. Okay, so even though I only draw a little bit of this graph, okay, what I want you to always think about is this actually does go on and on forever, okay? So put a little dot, dot, dot here to imagine that that is going to keep going forever, okay? Okay, so that's stretching horizontally and vertically. If we stretch vertically, what's it going to affect? The amplitude. If we stretch horizontally, what's it going to affect? The period. Okay, the period. All right, so, okay, yeah, I wanted to talk one more thing. So, yeah, of course, we've already talked through vertical stretches, shrinks, horizontal shrinks, stretches, reflections about the y-axis, reflections about the x-axis. What do we have left to talk about? That's vertical and horizontal shifts. Okay, so adding by a number on the outside. What's that going to do? It's going to take our whole thing, move it up 3 units. Okay, something like this. Okay, so this would be like 1, 2, 3 units to go up. All right, so that's pretty normal. I think you all have a pretty good understanding of that. The only thing we have to be careful about with a horizontal shift is that when we add by a number on the inside, how is that going to shift us? I'm going to go to the left. Pi over 2 units, something like that. Okay, so if I have a plus, I got to go to the left. So what is this going to be? This is going to be the graph of sine, but I'm going to move everything to the left, pi over 2 units. So I know there's somewhere where I did a decent job of graphing sine. There must be. Was it later on? Okay, here we go. I can use this, probably. Nah, I can't use that. Okay, we're going to do this from scratch. Okay, so how would I get the graph of sine? Well, what I'm going to do is I'm going to put on the relevant points. So if you want to be really careful, you can do like pi over 4, and then like pi over 2, and then like everything go by pi over 4. But I'm going to skip a little bit here. I'm going to skip 3 pi over 4 and go straight to pi. And then I'm going to go straight to 3 pi over 2. And then I'm going to go all the way to 2 pi. Okay, so let's do the graph of sine. Sine should have height 1 when? Height 1 at pi over 2. It should have height 0 at pi. It should have height -1 at 3 pi over 2. And it should have height 0 again at 2 pi. Okay, why is this? Because look at the unit circle. Trace along with me as we go from 0 up to pi over 2. What's happening to the height of the point as we go up? The height of the point is becoming 1. Then the height of the point is going to fall as we go to the input of pi. Once we get input of pi, what is the height of this point? It's 0. Then what is the height of the point as we keep going around? It becomes -1. And then as we go from 3 pi over 2 up back to 2 pi, we go again to a height of 0 at the end, okay? So that's how you know what it's going to look like. It's going to look something like this, okay? It's not a perfect drawing. So this is the graph. This is the graph of sine of x. But now we have to shift it. How do we shift it? To the left by pi over 2 units. So this point is at pi over 2. Where's it going to be transported to? It's going to go to the left pi over 2 units, which would take us exactly to here. So I'm going to draw this one using yellow. This point is going to get moved over here, yes? And this point is going to get moved over here, yeah? So it's going to look something like this. And we're going to pass through at pi over 2. Then we're going to go down to -1 at pi. And then we're going to go up to 0 at 3 pi over 2. And then we're going to go up to 1 again. Okay, so we did it. We did the horizontal shift. But I call this a special case. Does anybody see why this is kind of special? What have we achieved by moving the sine function left by pi over 2 units? Does the graph of this yellow curve look familiar at all? That's the graph of cosine. So it makes complete sense that if we move everything over to the left, if we move everything over to the left pi over 2 units, we're going to get the cosine function. Why? Because, look, the cosine function is kind of like if we were to take this whole thing, okay, and rotate everything by pi over 2 units, okay? If we were to take the whole unit circle, just pick it up and twist it like a driving wheel, right? To the right by pi over 2, yeah? If we did that, then the inputs would be all shifted to the left by pi over 2. And if we take this curve and just move it over slightly, we get this curve. Yes, if we just move it over slightly. Why is that? Because the width of the points as I go from here to here has the same process as the height of the points as I move from here to here. Okay, they decrease at the exact same rate, basically. Okay, so that's why when we take a transformation of sine, we can get back cosine. So this is actually equal to cosine of x. And also, if we take cosine of x and we move it, if we take cosine of x and we move it to the right by pi over 2 units, right? Move all this to the right by pi over 2 units, what are we going to get back? We're going to get sine. Okay, so these curves, even though they're different curves, they have the exact same shape. So when I move them enough, in just the right amount to the left or to the right, they will overlap with each other, which is why sometimes they call these curves sinusoidal. Okay, they call them sinusoidal, meaning they have the same shape. The shape is determined by the sine graph. Okay, so they say cosine is a sinusoidal curve, meaning that it has the same shape as sine. Okay, any questions on transformations of trigonometric functions? So stretching, shrinking, reflecting, and shifting. All right, it doesn't seem like there are any questions, so I'm going to move on to section 4.5. So new section, and we're going to talk about all of the graphs of all the other trigonometric functions, okay? So sine, cosine, and tangent we've already done, but we're also going to talk about secant, cosecant, and cotangent, and look at their graphs, okay? So before I do that, I wanted to help you have... Okay, anytime that I can, I want to see if I can give you multiple representations of the same thing. Okay, so I want to show you a couple other ways of visualizing the other trig functions. I think most of us at this point are confident with, okay, if I put the angle alpha in here, then cosine is going to be whatever this length is, right? And then sine is going to be whatever this length is, right? But how about tangent? How does tangent get visualized? Well, you can visualize tangent as if you were to draw a tangent line, okay, what is a tangent line? A tangent line to a circle touches at exactly one point. Okay, so there's a tangent line. We could do a tangent line here. We could do a tangent line here by drawing a vertical line, right? It would touch just barely at that one single point, okay? Just barely at that one single point. So it's just going to come in and barely kiss our circle and go off. So if you are to draw a tangent line, who touches the circle at exactly one point, and that exactly one point is the point which is pointed at by the angle alpha. Then, tangent of alpha can be visualized as the length of this line segment, okay? It's also the ratio, right? It's also the ratio of y divided by x, which happens to be also visualized by this length of this segment here. Now, you can imagine why, you can then imagine, using this intuition, one can imagine why the limit as x approaches pi over 2 of tangent of x is equal to infinity. Why? Because I'm looking at the length of this segment. It's nice and short, right? And then what do? We move up. It gets a little bit longer now. And then what do? We move up. It gets a little bit longer now. And what's going to happen to the length of this line segment when I'm very close here? It's going to have a super short slope, and it's going to go really, really, really far, right, before it touches the x-axis, right? So we're measuring how far until I touch the x-axis. Well, what's going to happen when I'm exactly tangent like this and I have a horizontal line? When is this horizontal line going to touch the x-axis? Never. Horizontal lines don't touch the x-axis unless they are on top of the x-axis, okay? So this is why you can imagine this line segment is going to get very, very long as the point here of tangency, the point of tangency is approaching this point on top of the circle. If we go all the way there, then we can't even say. If you want to answer, when does this horizontal line touch the x-axis? Well, you go to your math professor or your math instructor and you say, please leave off because that question doesn't make any sense, right? Okay, if I ever ask you a question that makes no sense, feel free to yell at me. Okay, so that's how we can visualize tangent. So some of the other ones we can also visualize, and I don't think it's really important to understand this, to be honest, but it is interesting, I think, to see it at least once in your life. So what is tangent? Tangent goes from here to here. So cotangent is going to be not the distance from this point to the x-axis on this line of tangency, but the distance of this point to the y-axis on this line of tangency. Okay, so that's what is going to be cotangent. So tangent goes from here to here. Cotangent is like the other piece that goes from here to here. So that's interesting. And how about secant? Well, secant is going to be the distance from the origin, or from the center of the circle, to the point at which the tangent touches the x-axis. Okay, the point at which the tangent touches the x-axis. And then what are we going to have? We're also going to have the cosecant. Instead of being the distance from where from the origin to where the point of the distance from the origin to the point at which the tangent line crosses the x-axis, it's going to be the distance from the origin to the point at which the line of tangency touches the y-axis. Okay, that will be the cosecant. Okay, so I think this is fun to see at least once, and in terms of, it's going to very easily show you why are the Pythagorean identities true, right? So what did we have? We had sine squared of t plus cosine squared of t is equal to 1. Why is that true? That's the Pythagorean identity for this triangle. Yes, this is a right triangle. And how about the other ones? What did we have? We had 1 plus, if I divide by sine squared, I'm going to get cotangent squared t. Divide by sine squared, I'm going to get cosecant squared of t. Why should this be true? This is the Pythagorean identity, not for this triangle, but for this triangle. If we look at this triangle, then what? The short leg is the radius, 1, right? So what are we going to do? We're going to take this one squared plus cotangent squared will be equal to cosecant squared, right? This is a hypotenuse thing. This is just Pythagorean theorem. And what's the other triangle you can see in here? It's this one. This is the other triangle. So what is this triangle going to tell us? It's going to tell us that 1 plus tangent squared of t is equal to secant squared of t. Why? Because here's one short leg, here's the other short leg, and what is the hypotenuse? The hypotenuse is secant. So the short leg squared plus the short leg squared equals the hypotenuse squared. This is nothing but the Pythagorean theorem for this triangle. Okay, so that's another different way in which you can visualize the Pythagorean identities. So I think that's kind of a fun way to visualize that. I don't personally really keep this memorized. Maybe I will from now on. But what I just remember is, yeah, there is some kind of like actual geometric interpretation of like what is secant, cosecant, and cotangent in terms of these lengths of these triangles that we put inside and outside of this circle. But I do think it's helpful to remember this one. The reason I think it's helpful to remember what the tangent is it's very easy to see when is the tangent going to be going to infinity or minus infinity. It's going to happen at this point and this point, right? Because that's when our tangent line is going to become a horizontal line. So it's easy to see the inputs which are going to cause tangent to not work out so well, right? Okay, so that's some more visualizations of the trig functions for you. I hope that by just giving you lots and lots of different interpretations of the trig functions, you'll be able to find the one that kind of clicks for you. And that will help you when it comes time for the exam. Any questions on this kind of visualization? Okay, doesn't seem like there are, so, okay. Let's talk about the graph of tangent of x. So, maybe it would be helpful if I took a little unit circle here. Let's copy that and put it, I don't know, I guess I need an extra page. And put it here. So we want to know what is the domain of the tangent function. Well, the domain is going to be all of the angles such that I can find the distance from that point to the x-axis. So the times when I'm not going to be able to do that are when the input is either straight up or straight down. Those are going to be the times where the tangent line doesn't touch the x-axis, and therefore they should be excluded from the domain because we can't answer the question of how long is this line segment here, because it's not a segment at all. It's infinity, right? Or negative infinity. So, so what do I want to exclude? I want to exclude pi over 2, and I want to exclude 3 pi over 2. And what's the next one? The next one would be if I went an additional pi around. So if I were to go one more pi around from 3 pi over 2, I would be at 5 pi over 2. Yes? And then if I were to go one more additional pi around, what would I be at? If I added pi to 5 pi over 2, I would get what? What would I get if I added pi to 5 pi over 2? How do I do that? Well, let's do it together. 5 pi over 2 plus pi. How do I reconcile this? To add two numbers where one of them's a fraction, what do I have to do? Find a common denominator. So I multiply the top and bottom of this one by 2. And what do I get if I do 5 pi over 2 plus 2 pi over 2? They have the same denominator, so what do I do with the numerators? Just add them, right? So what would I get in this case? Yeah, we would get 7 pi over 2. So you're probably starting to see a pattern, right? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. It's all of the odd multiples of pi over 2. Okay, so the way we can express that is odd numbers are all expressed as 2n plus 1. Take any integer n, multiply by 2, you'll get an even number. Add 1, it should be odd, right? So that's an odd number. So let me highlight that. This is an odd number. And multiply by pi, divide by 2, you will get an angle which points either straight up and down, or straight up or straight down. Those are the options for these guys. So these are the numbers which we should exclude from the domain of the tangent function. They are going to be where I have the asymptotes of this function. Okay, and how about the range? Well, we already took a look at what the tangent function looks like. It looks something like this, right? It kind of looks like x cubed, doesn't it? Kind of looks like x cubed. Well, what is the range going to be? Well, we have on the left side, we're going down to minus infinity. So we go from minus infinity. And then on the right side, what are we doing? We're going up to positive infinity. And we hit everything in between. So all the numbers between negative infinity and infinity, we call that the real numbers. Okay, so that's the range of the tangent function. And how about the zeros? Well, remember, tangent of x is just equal to sine of x divided by cosine of x. So when is tangent going to be 0? Tangent is a fraction. A fraction is 0 when the numerator is 0. So the tangent function will cross the x-axis. The graph of the tangent function will cross the x-axis at those points which sine crosses the x-axis. Because the numerator of a fraction is 0, the whole number is 0. Okay, and like I have already kind of described, the period is going to be pi in this case because, of course, if we take any diameter, then the relationship of these points will be, one of them will be xy, and the other one will be negative x, negative y. And then what are we going to get when we divide them? Well, the negative signs will cancel, and we'll get the same thing. Whether we take the ratio of these points, these coordinates, or the ratio of these coordinates, we will always get the same thing, which is why the period of tangent is pi instead of 2 pi. So it repeats more often. Okay, so that's all I want to say about the graph of tangent. Okay, so here's the picture. Like we said, here's the picture. So sine of 0 is 0, so tangent should be 0 as well, at 0. And then if we go to the right, what's happening? Sine is getting close to 1. When we get to pi over 2, the numerator will be something like 1. And the denominator will be something like whatever cosine's doing, which cosine's going down to 0. So the denominator will be, well, numerator will be something like 1. Denominator will be something like positive small. So this gives us positive big number, right? So this is why the tangent function has an asymptote here, goes up to positive infinity. On the other side, we have the opposite behavior, okay? The other side, we have the opposite behavior. And we just do this over and over again. So I put dot, dot, dot here, meaning it goes on and on forever in the left and in the right direction. And the height will be repeated on intervals of pi, okay? So again, another interval of pi, another interval of pi. We're going to, again, have the same height. Another interval of pi will have the same height, okay? Any questions on the graph of the tangent? We spent a decent amount of time talking about that now. I think it's one of the more confusing ones to graph, for sure, because of those tricky asymptotes. Okay, if no questions, then just know that we can do the usual transformations, okay? We can stretch, we can shrink, we can reflect, and we can shift. Okay, so a vertical shift, what would we do? We'd go like up 3 units or something like that, and we would draw this like this instead or something like that, you know? or we could move it to the right, move it to the left, compress it, or whatever. So I'll just pass to our previous lecture if you want to see that. So okay, let's look at this one. So example, if you had this, what kind of transformations do I have? Also, we got to remember the order, right? So horizontal shift, that's first. Then next, we also have a horizontal, what does that 3 do? Horizontal compression, yeah, or shrink. Compression or shrink, because this is a number bigger than 1. And then what do we have? We have a vertical stretch by a factor of 2 and a vertical reflection, okay, about the x-axis. And then finally, vertical shift down 17. Okay, so that's just going back to that section we did on transformations. Okay, so now I'm going to talk about the reciprocal functions, okay? So what do we mean by reciprocal? Well, cosecant of x is the reciprocal of sine. Secant x is the reciprocal of cosine. Cotangent of x is the reciprocal of tangent of x. Okay, so what we mean by reciprocal is we take 1 divided by that function. Okay, so what are their graphs going to look like? Well, first of all, let's talk about the domain. I'm lucky that for some reason the thing is not showing up today, so you can actually see what the domain is. Okay, so why all real numbers except for n pi? Why is n pi not going to be in the domain of cosecant? Why should we exclude n pi from the domain of the cosecant function? That seems like a strange thing to do. Well, what does n pi look like? If n's an integer, pi is pointing where? Straight to the left. Here's pi. And how about 2 pi? That's pointing straight to the right. Here's 2 pi. And then also 3 pi. Where's that one pointing? Straight to the left again. Here's 3 pi. And then 4 pi is again pointing to the right. So whenever we have n pi, this is going to correspond to this, like one of the points either here or here. Why should that be excluded from the domain of the cosecant function?
Because sine is 0.
Is that what you were going to say? Yeah, so sine is 0. Exactly. Why is that a problem? Because cosecant is defined by 1 divided by sine. Okay? In other words, if we point straight to the right, or if we point straight to the left, these points have -1, 0, and this is 1, 0. What do they both have in common? The y-coordinate is 0, which means that sine would be 0 if we plug in one of those angles. So if we plug in n pi into the sine function, we would get 1 divided by 0. So now you have an idea of why we should not include these numbers in the domain of the cosecant function. Anytime that we're talking about the domain, we have to exclude those numbers which would cause us to divide by 0 otherwise. So what are we going to avoid doing for the secant function? We don't want the cosine to be 0. When is the cosine 0? The cosine is 0 when the angle points either straight up and we get the point 0, 1, or if it points straight down and we get the point 0, -1. And what kind of angles are going to produce these points on the unit circle? Well, pi over 2 would do it, or 3 pi over 2 would do it, or 5 pi over 2 would do it, or 7 pi over 2 would do it, and so on and so forth, right? So on and so forth. So we don't want cosine to be 0 when we're doing the secant function because we're going to divide by cosine. We don't want to do 1 divided by 0, so we have to exclude those inputs which would cause the denominator to be 0. Otherwise, we can plug in anything we want. Okay, likewise for the tangent function, why is it that the domain of the cotangent function is going to be the same as the domain of the cosecant function? Why is that true? Why are these domains going to be the same?
Both have sign in the denominator.
Exactly. Both of them have sign in the denominator. That's a very concise way of putting it. In other words, tangent, remember tangent will be 0 whenever sine is 0. Because 1 over tangent here is going to be what? Cosine over sine. So they both have sine in the denominator, which is why the domain will be the same. We have to exclude those numbers which would cause sine to be 0. That's a very concise way of putting that, Sully. Nice job. Okay. So these are the domains. How about the ranges? Okay, well, the ranges are going to be a little bit funky. Okay, why is the range of the cosecant function going to go from negative infinity up to negative 1 and then from 1 to infinity? That seems kind of weird, right? Well, the way you can think about it is, what is the range of the sine function? Sine of x has range, what? What are the possible y values that can be created by sine? Well, sine function, remember, looks like this. What's the tallest that it could be? 1. What's the smallest that it could be? Negative 1. So the range of sine is? Yeah, or negative 1 and 1, right? And we're going to include those because there actually is a point which would cause these to be true, right? Okay, so this is the range of sine. So think about all of the possible numbers which I could create by dividing 1 by one of these numbers. And you'll see why I can never have something which is between negative 1 and 1. Why? Because to have a number which is between negative 1 and 1, let's say something like 1/2, what would I need to do? I would need to divide 1 by 2 in order to get 1/2. But sine can never be 2, can it? So that's why we're going to exclude this middle region of points, because the absolute value of sine can never be larger than 1. So we're taking 1 divided by something which is always less than 1 in absolute value. And so then we're not going to ever be able to create like a fractional value by doing that kind of division. We can, however, allow the denominator to become very close to 0. If we allow the denominator to become very close to 0 and positive, what kind of number would I get? If this sine of x is 1, so if we do 1 divided by very small positive number, what kind of number will I get? If I divide 1 by a very small positive number, yeah, Lily?
Very big number.
A very big number, and what would be the sign of that number? Very big positive number. Very good. So if we allow sine to be something like 0.000001, right? That's in this interval. We can take a number very close to 0. Then what's going to happen is that 1 over sine is going to blow up to positive infinity. And if we allow ourselves to approach 0 from the negative side, okay, so something like negative 0.000001, then we can get a very, very big negative number, okay? As big as we want. So the range will go from negative infinity up to negative 1. We can't do anything between negative 1 and 1. And then we can go from 1 up to infinity, okay? So the story of secant is going to be exactly the same. Why is it exactly the same? Because not only does sine have range negative 1 to 1, but cosine of x has the same range as sine, right? It's just the same function moved over a bit. So the heights are going to be the same, okay? The heights are going to be the same. All right, so that's the range. And then, okay, cotangent. Remember, tangent can be any real number, right? Could be any real number because we can hit all of them. All of the heights are possible. So we take 1 divided by any real number, we're going to get, again, all of the real numbers. Because if I want to achieve 1 million, I just need to divide 1 by 1/1,000,000th, right? Something like that. Or to achieve 1 over 1,000,000, I just need to allow tangent to take value 1 million, which is fine. Okay, so that's the domain and range. How about the period? Well, same period for the reciprocal sine, reciprocal cosine, and reciprocal tangent. We'll have the period of tangent, which is again pi. Okay, so yes, you can find the x-intercepts if you want. Well, these ones aren't going to have any. Yes, you can describe whether they're going to be even and odd. We already talked about which ones were even and odd, actually. The even and oddness is going to be inherited by the parent function. So sine is odd, therefore cosecant is odd. Cosine is even, therefore secant is even. Tangent is odd, therefore cotangent is odd. Makes sense. But what are they going to look like? Well, I'm going to show you now. These are what they're going to look like, and I will describe how we can understand why they're going to look like this, because these look very funny, don't they? They look funny. That looks weird. Well, what are we seeing here? This is the graph of sine. How do I get the height of the... Let me change my color pen to something that's going to stand out. How about purple? Okay, so if I am to take this input, okay, how am I to find the height of the cosecant function? What I must do is take this height, whatever this height is, so if this point has x, y, right, then sine of whatever this input is, okay, we have that sine of x is equal to y, yes? Sine of x is equal to y. So what would then cosecant of x be equal to? Not y, but 1 over y, which is 1 over sine x, which is 1 over sine x. Also could write it like that. So how do I get the height of this point? I take 1 divided by the height of this point, and that will give me this point. So you can imagine, as the denominator goes to 0 from above, what's going to happen to the reciprocal? It's going to go up to infinity. What happens if the denominator of the fraction 1 over sine x, what if the denominator goes to 0 from below? Then the fraction will go to minus infinity. Okay, so another way that you can think about this is if you wanted to just have a cheat, okay, if you wanted to just have a cheat, is that these two functions are going to touch at the peaks and valleys. Okay, these two functions are going to touch at the peaks and valleys. And you know that cosecant is never going to cross the x-axis, so you know that we're going to have a u. If it touches a peak, it has to be a u. If it touches a valley, it has to be an n. Okay, or whatever, something like this, right? So why are they going to touch at exactly this point? Why should they touch here? Because this is the point where 1 over sine of x would be equal to 1 over 1, which is 1. So because the denominator is 1, the whole fraction is 1, and so the denominator is equal to the fraction. Okay? How do we feel about this graph of cosecant? Kind of tricky, right? But what I want to say is that you will never feel like this is too hard. What I don't want you to do is look at this and say, wow, that graph looks complicated. I can't believe I'm going to have to memorize that. No, don't memorize that. I'm telling you not to memorize that. what I hope you will feel confident with is I am confident in my ability to draw the graph of sine and cosine. If you are confident with your ability to draw the graph of sine and cosine, then you only need remember that I'm going to draw sine here. I'm going to draw sine here. And I know that cosecant is just the reciprocal of the height. Okay, you remember that it's the reciprocal of the height. And if you remember that, then you can just say, well, I know how to draw sine, and I know how to find the reciprocal of a number. If you know those two things, you can draw the graph of cosecant, can't you? Because you just need to imagine, well, what is going to happen if I divide 1 by 1? I will get 1. What if I divide 1 by 1/2? What am I going to get? If I do 1 divided by 1/2, what would I get? 2, right? Because dividing by 1/2 is the same as multiplying by 2 over 1, right? So if I divide by 1/2, what am I going to get? I'm going to get 2. So that's how I know that this height should be 2. And then again, what's going to happen as we go further down? We're going to divide by numbers like, I don't know, we're going to do like 1 divided by 1 over 1 million. Something like that, right? And what do I do then? I multiply by 1,000,000 instead of dividing by 1,000,000. So then the height is going to be like 1,000,000, yeah? So just remember how to graph sine and cosine. If you can do those, then all you have to do is fill in what does the graph of the reciprocal look like. You fill in what does the graph of the reciprocal look like by, you know it should look like u's and n's, and they should touch the peaks and valleys and stay on their respective side of the x-axis, okay? Stay on their respective side of the x-axis. Any questions on graph of cosecant? All right, then what is the graph of secant going to look like? It's going to be the exact same thing, except our reference point will not be the graph of sine, but the graph of cosine. Okay, we'll draw cosine, and then we'll make these u's and n's in the respective way. Okay, but the only difference is we're starting from a graph of the cosine function instead of starting from the graph of the sine function. And for cotangent, I know this looks really strange, but let me see if I can try to motivate this. Remember, we're doing the reciprocal. So when tangent gets close to 0, what kind of behavior will that produce for the reciprocal? Well, I'll be getting close to dividing by 0. So if I'm going to have a vertical asymptote for the reciprocal of the tangent function at any point at which the tangent function will be 0. Okay? So tangent is 0 when the input is 0, and therefore we observe this kind of asymptotic behavior of the cotangent function when the input gets close to 0, because we're dividing by tangent of x. If we take the x value, which is going to cause the denominator to be 0, it's going to cause a problem for the reciprocal, right? Okay, and when is the cotangent function going to become 0? The cotangent function will become 0 when the tangent function becomes infinity. Okay? Because you can safely say that 1 divided by infinity, okay, I'm committing a math crime here, but I'm going to say this is equal to 0. It's only really a math crime in higher math, so I will commit math crimes for you because you're my favorite students. Okay. So the cotangent function will become 0 when the tangent function becomes infinity. Yes? Sure. I'll put them all on the screen. Like this. How about that? So, okay, I'll explain what do I mean by math crime. Is cotangent strictly speaking, if we define it as the reciprocal of the tangent function, then 1 over tangent is not defined whenever x is like pi over 2 or a multiple of pi over 2, an odd multiple of pi over 2. So strictly speaking, we're not doing 1 divided by infinity, we're doing 1 divided by something which isn't even defined. So to say that 1 divided by something undefined is 0 is, So it's not good to talk like that. But nonetheless, this is how the cotangent is defined, because the cotangent will be equal to the reciprocal of the tangent function as long as the tangent function is defined. And at those couple of points, these few 0 points, we define it in a different way. We just say, well, I'm going to say it's 0. Or we take the geometric interpretation of it, right? We take the geometric interpretation, like that distance from like the tangential point, the point of tangency to the y-axis. Okay, we can view it that way too. Can I move on from this screen now? Or we need a little more time? Okay, so again, I mean, I think it's maybe worth memorizing, like, oh, generally speaking, I know what the graph of cosecant and secant look like. They look like a bunch of u's and n's. And the graph of the tangent function looks like kind of the reverse. It's going from top to bottom instead of like the tangent, which goes from bottom to top. Okay? And it's going to look a little bit different. But just generally, you can memorize like just the general shape of these guys, and then you can just remember, well, I know what the graph of tangent looks like. I can graph tangent, and if I can graph tangent, then I can easily graph 1 over tangent. Well, not easily, but I can do it. I believe that you can do it. So the ones that you should spend a lot of time or a lot of effort memorizing are the graphs of sine and cosine and tangent. Okay. So what else do I want to talk about? I think what I want to do is stop there for today. So yeah, we've done enough. We went through a lot there. So have a nice weekend, early weekend, by 4 minutes.